We're skipping 10.4 and going into 10.5, which is actually going to be something a little familiar to us. We're just gonna have to keep it all straight. Angular kinematics. So kinematics was our very first unit, if you guys recall. This was the position, velocity, timeless formula, all of those. We can actually do those types of formulas and those types of questions talking about, they say angular motion or rotational motion. And they look very similar, almost exactly like our normal formulas. What just happens is basically we replace with the variables that we're working with angular motion. So theta here is actually angular position, or if you want to write this down as well, angular displacement. So if they're asking for that, or if they say the angular displacement is this, that's actually theta. So instead of x, which we normally use for position, it's going to be theta. So omega, we remember, is the angular velocity. So again, instead of v, we already know this because we've had to do it a couple times now, we have the omega. And don't forget that this is change in theta, angular position, over time. Now we have one more new variable here. When we're talking about angular acceleration, that's alpha. Looks like a little fish almost, or an A with a little like blip on the end. That is the angular acceleration. And that is the change in angular velocity over time. Keep in mind that, again, all of these things are going to be in radians in order for these formulas to work. Let's fill in a little table here. So to refresh our brains, these were our linear motion formulas. What we're going to do is we're going to replace these formulas with our variables again. This is position, velocity, and acceleration. So I want you to take a moment, rewrite the three formulas, replacing with those variables, and then you can click continue to check. Okay, so we have now that omega is what we represent for velocity. So we have omega final equals alpha times time plus omega initial. And again, that's just angular velocity final, angular acceleration, Time is just still time, right? That's not angular, that's just seconds. Now again, we talked about how angular velocity is the same at all points. That's specifically referring to an object that is rotating without acceleration. Now we're saying that we're speeding up. The angular velocity is going to change at that point. So we don't mean that, oh, it's different angular velocities at different points. We're talking about with acceleration, we have different angular velocities. So position again, now it's theta final. So if you didn't have little subscripts in there, the subscripts are still there. So this is the final. So if we started here, for example, that'd be like our initial angle. If we ended there, that's our final angle. So we have 1/2. Again, acceleration is now alpha times time. Oh, I'm sorry. I just realized I did the wrong subscript. That should obviously be a squared. There we go. Plus v again is now omega, angular velocity, t, plus x again is now our angle. Because we're talking about an angular motion, our position is based on the angle we're at. And then lastly, we have omega final squared equals omega initial squared plus 2 times alpha, theta final minus theta initial. So the formulas are actually the exact same. It's just, it is a little bit confusing because, especially when dealing with the angle, we have to be careful and remember that that's position now, as well as that, which we're going to have some reminders down here. Working with radians is kind of tricky to keep it all straight. So a couple little reminders here as well. We have the same thing with the averages. If we're talking about an average velocity over a certain amount of time or the average acceleration over a certain amount of time, same thing is going to happen where we have the angular velocity average is going to be what again is now our position variable, theta. Now we know this formula already because we actually already did this formula in lesson 1, I think, lesson 1 or 2. And for acceleration, which is again, which variable? Alpha now. That's angular acceleration is change in V, which again is our omega, divided by change in time. So same formulas, it's just now we're dealing with angular concepts. Now, oh man, my blank is not there. That's okay. I forgot to do this one. Actually, I can do it real quick. Now I'll just cut this out. Granted, you have to copy the whole thing, but I like that it has you focus on the important things. Okay. Okay, so lastly, so there's a couple of kind of key points you want to write down. Okay, lastly, there's a couple key points that you're going to write down as well. There's going to be a slight difference in the questions asked. Again, they might say, what's the angular velocity? Solve for omega. What's the angular acceleration? Solve for alpha. But if they say how many revolutions or rotations, or what is the angular displacement? Remember, that means now that they're asking for theta. They're not necessarily going to say, what is the position? What is the distance traveled? That would be different. If they say angular displacement or revolutions, rotations, this is theta. It is possible they could ask a question like, what is the distance traveled? But it would be more of like the circumference, like how long the circumference is, I guess, and how many times it's traveled to be based on that. So if they say how many revolutions, rotations, we're solving for theta. Now keep in mind that they may give, and very often, they give the acceleration and velocity units as revolutions. We know that we've had to practice with that where we go from revolutions per second to radians per second. Now, again, to use these formulas, for these formulas to work, actually, it has to be in radians per second. If we don't have it in those units, then it's not going to work out. I will say, if your answers have it in radians per hour or radians per minute, you can leave the time like that. But for theta, it has to be in radians. However, we can do our calculations in radians, but sometimes based on how the question is being asked, you might actually need to convert back to revolutions in your final answer. But again, we can't get around not converting to radians. You have to convert to radians in order to use it in the formulas. Otherwise, the math actually doesn't work out. Okay, so let's go ahead and look at one question. We're going to do these very similarly to how we did these kinematic formulas, where we've got 6 different possible variables, yeah, which we're going to go over in just a second. I'm going to give you a second. If you want to jot this down, you can, and then we'll come back and we'll go from here. So a car is accelerating, causing an angular accelerations of its tires. So this is talking about, again, the change in the angle over time squared, I guess you could say, or the change in the angular velocity over time to be this. So this is not talking about the car accelerating. This is actually the tires themselves speeding up in how many revolutions they make in a second, yeah? So we have the initial angular velocity of the tires before it started accelerating. So just kind of putting along. It had half of a revolution per second. So if you can imagine a tire on a car, this literally means it turns halfway each second. So there goes 1 second, 2 seconds, yeah. That would be your tire rotating. We want to know the angular velocity after 10 seconds of acceleration. We want to give the answer in both radians per second and revolutions per second. Hello, my boy. So let's attack these like we attacked the kinematic equations before. We have 6 different variables here. 1, 2, 3, 4, 5, sure. So we have, and then this is kind of painful, but we have omega final. Remember, that's our angular velocity final. We have omega initial. We have alpha for acceleration, we got time. And then for position, remember, position is theta final and theta initial. So remember, we have these 3 formulas to work with as well as these 2. Don't forget about these. If you're looking at a problem and you're like, I swear I don't know how to, I can't use any of these, it might be the average formulas you're using, so be careful with that. So what we're going to do is we're going to see what variables we have. We're going to look at our formulas and go, okay, what formula can I use based off the variables I have, as well as what I'm trying to find, plug in and go from there. So I want you to take a moment and see if you can tell. We've got 1, 2, 3, and then this is our what? We have 4 of these variables given to us here. Try and fill them in. Okay, so angular acceleration, that's alpha. Let me actually pause real quick. Before we do this, I should be careful here. Let's go ahead and do, actually I lied. Yeah, I think I'll do that with conversions. Okay, so what I kind of decided to do here, we're going to go through and label the numbers. We do need to convert to radians per second to do our math. So I'm going to first list them out in revolutions per second, and then we'll do a conversion to radians per second, and that'll be in our next one. Okay, so you should have gotten 3, 4, that's the angular acceleration, that's alpha, yeah. Now again, that's revolutions per second. We're gonna do another conversion to radians. We have the initial angular velocity, which is omega initial. That's gonna be 0.5, and that is also revolutions per second. It says, what is the angular velocity? So what is the angular velocity after a certain amount of time? They are asking for our angular velocity final, that's your question mark, after 10 seconds. So looking at our variables, what we have, let's look back to our formulas. Which formula can I use to solve for angular velocity final, omega final? That's going to be our velocity formula. We have 1, 2, 3, 4. We have all 4 of these variables. Or again, we're looking for this one, but we still technically have it. So we're going to use the velocity formula. So I'm going to go ahead and copy it over, and then we'll go ahead and do our conversions. Okay, so I want you, these are all in revolutions per second. We need to convert them to radians per second, which again is not going to be hard because we only have to convert away the revolutions. Go ahead and do it real quick. So what you should have done is just multiply by 2 pi to get to radians. Since it's already in seconds, we don't have to divide by anything to get from hours to seconds or minutes to seconds. So I'm going to go ahead and get these as decimals. So 0.5 times 2 pi is, oh, that makes sense, 3.14, because that's half of 2 pi, which is just pi. We have 3 times 2 pi, which is 18.8. I'm going to go ahead and actually do these all as 2 decimals, 0.85. And then we have seconds. Careful, I almost did that. This is good to go. That's already in seconds. Don't change that to pi. Yeah. Okay, so I got those conversions. So all I got to do is plug in these numbers here. This is going to give my answer in radians, and then I can go back to revolutions per second. So let's go ahead and give this a shot. Let's plug this in. We got angular velocity final equals, my alpha is 3.14. Nope. 18.85. My time is 10. My initial is 3.14. So all we got to do is pop all this in. We got 18.85 times 10 plus 3.14. We should get a final angular velocity of 191.64. Did I plug that in right? Yep, that should be it. Now again, this is in radians per second. So I want you now to convert back to revolutions per second, just so we can see how we would do that. We've done so far a conversion from revolutions to radians. Now we're going in reverse. So think about how I would undo this. Well, if we went from revolutions to radians and multiplied by 2 pi, to go in reverse, we're just going to divide by 2 pi. So 191.64 divided by 2 pi, we should get 301. Do I have this correct? 191.6. Ooh, 191.64 divided by 2 pi. Oh, 191.64 divided by 2 times pi. There, pizza. Oh man, 2 pi. There we go, for Pete's sake. Okay. Careful with plugging that in. I didn't put parentheses around 2 pi, so it came out funny. So in revolutions per second, we have 30.50, so 30.5. That's revolutions per second. So again, to go from revolutions to radians, multiply by 2 pi. To go in reverse, divide by 2 pi. So we're going to try one more question. This one's going to be a bit trickier now because this was just a straightforward use one formula. But if you recall from way back when, there's some times where we have to use multiple formulas. So let's go ahead and give this one a shot. A top spinning at 4 revolutions per second comes to a complete stop in 64 seconds. Now, I'm actually going to do this right now. I should have done it in the beginning in the other one. Go ahead and convert that to radians per second. Okay, so 4 revolutions per second. Again, that's 4 rev per second. To get to radians per second, all I have to do is convert the radians. So I have 2 pi radians. Good Lord, I'm making so many mistakes right now. Hopefully no one watches this on YouTube. 2 pi radians per 1 revolution. So that cancels out. So all I need to do is 4 times 2 pi. We get here that this is 25.13 radians per second. Okay, it comes to a complete stop. Go away. Go away. Comes to a complete stop in 64 seconds. So obviously there's our time. Assume the top slows down at a constant rate. So that means there is acceleration and it is slowing down. How many revolutions does it make before coming to a stop? So this question, how many revolutions? What variable are we going to solve for? We wrote this down before. That's theta. How many revolutions means it's asking you to solve for theta. So let's go ahead. Let's lay out our variables like we did before. We've got omega final, omega initial. We've got alpha for acceleration. We got t. And then we have theta final and theta initial. Okay, so I want you to try it first. We already said this is what it's starting at. This is its initial, I kind of gave it away there, in radians per second. Good Lord. Okay, that's our, in radians per second, that's what it starts at. It slows down and comes to a stop in 64 seconds. Try and lay out which variables we have. You might need to check if you're unsure, but that's okay, we'll give it a shot. Okay, so this is its initial angular velocity. So 25.13 is actually its initial because it starts spinning and then it comes to a stop, which means its angular velocity final is 0. It comes to a stop, right? Now, we know there is an acceleration, but we don't know what it is. It just says assume the top slows down at a constant rate. We are looking for how many revolutions, I know I skipped something, does it make before coming to a stop? So this is saying this is our end goal. How many revolutions final? Remember, guys, that if they ask for a final position and don't give us an initial position, we can automatically assume it's 0. So there's our initial angle, 0. We're looking for theta final. And there's one more thing, we have that at 64. Now here's the thing again, as you're looking at this question. We don't know the acceleration, or in this case, it's going to be negative acceleration. We do know it exists because the top slows down at a constant rate. Even though theta final is my end goal, if we notice in all of our formulas, I have acceleration, acceleration, acceleration. I can't use any of these formulas without knowing the acceleration. So what we can do is we can use one of these formulas to solve for acceleration, and then we can go back and find what we're actually trying to find. So look at what we know. How could I solve for the acceleration here? There's kind of two different ways you could look at doing it. But let's go ahead and look at our formulas here and think, how could I figure out what the acceleration is? Now, again, there's two ways you could do this. You could use the velocity formula because we know all of these. We know this, we know time, we know this. Really, doing the acceleration average formula is actually going to be the exact same. The change in W, that's the W final, sorry, omega final minus omega initial over the time. Using the velocity formula versus using this is actually the same thing. So I'm going to go ahead and use the velocity formula just because I prefer to think of it that way. We have omega final equals alpha t plus omega initial. So again, I want to solve for this so that I can eventually solve for theta final. Can't use any of those formulas if we don't know angular acceleration. So go ahead and plug it in, solve for that acceleration, and then see if you can go from there. Try and keep going, see if you can figure out what formula we're going to use after this in order to get our theta final. Okay, so let's see. So we've got a 0 here for final. We're looking for the acceleration. We got time of 64 seconds plus 25.13 for our radians. So solving this, you should have gotten, let's see, negative 25.13 divided by 64. So we should get an angular acceleration of negative 0.39 I'm going to use. And again, this is in radians per second squared. Okay, so now that we know that, and it's negative because it's slowing down, now we can look at our variables and see, okay, what can I use now in order to solve for omega final? Well, looking at our variables we can use now the position formula. If I'm trying to find omega final, we can use this one to solve for it. Technically, you could use the timeless one as well, but we know time, so we're going to go ahead and use the position one with time. So we've got omega final equals 1/2 alpha t squared plus, theta final, I'm messing everything up. Omega initial t plus theta initial. There we go. Be very careful. Pay attention to what I'm writing, not what I'm saying. Okay, so we're going to go ahead and plug everything in here. Keeping in mind there's going to be an easy way to do this. So I'd recommend pause. Oh. No, we're going to have to. Oh, no, this will be easy. I lied. This one will come out nice and simple. Go ahead and give this one a shot. Okay, so I'm trying to find omega final. That's theta final. I keep saying omega. We got 1/2 alpha is negative 0.39. Time is 64 squared. This is going to be quite a bit. Plus our initial angular velocity is 25.13. Times our time is 64. And we do not have, again, an initial starting point. We're looking for just how many rotations it goes through. So we just got to plug everything in here. 0.5 times negative 0.39 times 64 squared. It's going to give us a pretty big number. Plus 25.13 times 64. Okay, so you should get a theta final. Now keep in mind that this is in radians as our final answer. Let's look back up to the question though, because they ask for how many revolutions. So this is what I warned you about. We have to convert to radians to plug into these formulas. It doesn't work out the way we need it to if we don't use radians. However, we are looking for how many times it turns around before it comes to a stop. So we just talked about this. If I want this now for revolutions, how many revolutions would this be? If normally, to get from revolutions to radians, we multiply by 2 pi. I'm going backwards from radians to revolutions. Go ahead and try it. So we should divide by 2 pi. If we're going in reverse there, being careful to put this in parentheses. Okay, so we should get 128, let's go ahead and say 0.85 revolutions. So that means that this top spins around 128 times, 0.85, yeah, before it comes to a stop. So we're going to try again some slightly more complicated questions. The tricky part is keeping your radians and revolutions straight, as well as not getting things mixed up, as you heard me say over and over again, and I'm not re-recording this video, so it is what it is. I kept saying the wrong things. I was writing the correct things, but I kept saying omega instead of theta, so forth and so on. So just being careful. We're going to do a couple more practice problems together, and then you guys can try the assignment.